Good morning. Today, I'd like to talk about two more convergence tests for infinite series. These tests involve comparing one series against another, and in certain circumstances, if we know the behavior of one series, we will know the behavior of the other one. The direct comparison test says this. Suppose you have some numbers, AI and BI. The AIs are all positive. The AIs are all less than or equal to BI, which means, of course, the BIs are all positive as well. Statement number one, if the sum of these terms converges, then the sum of those terms converge. If the sum I equal 1 to infinity bi converges, then the sum I equal 1 to infinity ai converges. Second part, if the sum of the numbers in the middle diverges, then the sum of the outside numbers diverge as well. Just like before, it's very important to understand that when we say stuff like this, we say what we mean exactly, but not anything else. We have no sentence here that starts off with, if the sum of the AIs converge, then something happens. We know this statement, we know that statement, but the direct comparison test doesn't say anything else. As an example, let's think about the sum n equal 1 to infinity, 1 over 1 plus n squared. I'd like to know if that converges or not, and maybe I can use my direct comparison test to figure this out. Observe, you could also figure the answer to this question out by doing the integral test. The antiderivative of 1 over 1 plus x squared is arctan x. In any case, I'm interested in this comparison test. So I look at these terms and I think to myself, do I know an infinite series that is similar to that, but the terms are related to each other in an ordering kind of way? 1 over 1 plus n squared is 1 divided by a number that's bigger than n squared. 1 over 1 plus n squared is less than or equal to 1 over n squared. And of course, these are all positive. We need to relate this back to the body of knowledge that we've developed so far. Do I know if the sum 1 over n squared converges or not? The answer to that question is yes, because it's a p-series with p equal to 2. I know that because I know the integral test. If I want to write that down as a careful logical statement that says exactly what I mean, but not anything else, I can say it this way. Since the sum n equal 1 to infinity 1 over n squared is a convergent p-series with p equal 2, the direct comparison test tells me that the sum n equal 1 to infinity 1 over 1 plus n squared converges. Notice that I don't know what value that series converges to, but I do know that if you add on enough terms in the infinite series, the partial sums begin to look more and more like some particular number or the other. Speaking of that p-series with p equal 2, I can use it to illustrate a particularly bad choice. Since n is 1 or 2 or 3, and so on, n squared is at least as big as n is. 1 over n squared is no more than 1 over n. What the direct comparison test tells me is this: if the sum of these quantities converge, then the sum of those quantities converge. Unfortunately, the sum of those doesn't converge, so that part of the direct comparison test does not apply to this. The second part says if the sum of the quantities on the inside diverge, then so do the sum of those quantities. But if I didn't know about this series already, I wouldn't know that if this converges or if it diverges. Both parts of the direct comparison test in this particular case fail to tell me anything. This is a good place to mention the after a while effect. The hypothesis for the direct comparison test says that there's a certain ordering between the terms of the two series, and that ordering should always be true for all relevant indexes. Strictly speaking, that's not true. So I want to think just for a moment about a situation where I have two infinite series with the special property that after a while, after some particular index, capital N, the BI number is the same as the AI number. I'm going to think about a partial sum for each one of these two things with some index that's larger than this capital N. I'll call the partial sums of this series capital S, and I'll call the partial sums of this series capital T. If you write out partial sums for these two things, where the k again is bigger than n, S number k will be a1 plus a2 out to an, and then more terms, an plus 1 out to wherever it is you decided to stop. Likewise, tk is b1 plus b2 plus bn plus bn plus 1 out to bk. In the situation that I'm thinking of here, though, if the index is capital N or bigger, the b number and the a number are the same. Taking advantage of that fact, I can write this formula down, and I'm going to think about this versus that. If k is bigger than n, then sk minus tk will be that quantity minus that quantity plus this quantity minus that quantity. Those cancel each other out. I'll call this number minus that number capital C. So this says that sk minus tk is a constant that doesn't depend on which exact value k that you pick. This says that sk is c plus tk if the limit of the partial sums for the B series converge, then so does the partial sums for the A series. You could rearrange this and say that tk is sk minus c and draw the same conclusion. So, for example, in the direct comparison test, if it was true that this required inequality wasn't really obeyed for all indexes, but was obeyed after a while, that would be just as good. In the integral test, if the f function isn't always positive and decreasing, but it was beyond some particular index, that would be good enough too. Suppose that you had figured out that a sub capital N plus the next a number, so on and so forth, out to ak, and then take the limit as k tends to infinity. Suppose that you found out that that infinite series converged. You could think of this as being the B series, where the first capital N minus 1 terms in the B sequence are all 0. From what we've just said, convergence or divergence of an infinite series is not affected if you alter a finite number of terms. So if I know that that infinite series converges, then I know that that infinite series converges as well. If this one diverges, then so does the other one. Even so, that requirement that at least after a while that inequality be true is a severe hamper when you're trying to use the direct comparison test. There is another comparison test that we can use. This is called the limit comparison test. I'm going to assume that the A numbers and the B numbers are positive, or parenthetically, positive after a while anyway. I'm going to look at the limit as n tends to infinity of an over bn. If that limit exists and is a non-zero finite value, then this infinite series and that infinite series either both converge or both diverge. This will be a lot easier to use than the direct comparison test because there's no need that the A numbers have to be smaller than the corresponding B numbers. As an example of how you use this kind of thing, I want to think about the sum n equal 1 to infinity of n squared plus 5n plus 1 over n to the fourth plus 3n squared plus 2n plus 4. Here's the idea. I'm going to think about how this acts, roughly speaking, when the index n is extremely large. This should suggest to me an infinite series that I can use this with in the limit comparison test. So let's just think about this for a minute. When n is really big, n squared is going to be much bigger than 5n, much bigger than 1. Likewise, when n is big, the n to the fourth power term is going to be much bigger than 3n squared, or 2n, or 4. I suspect that if n is very big, the things that I'm adding up look very much like what I would add up if what I was doing the infinite series of was just n squared over n to the fourth power, which is 1 over n squared. I suspect it will be revealing to try out this limit comparison test with the sum n equal 1 to infinity 1 over n squared. I have to emphasize, though, this is just a suspicion that I have based on the algebra. I don't know if this is going to work or not. I have to carry out the calculation of the limit involved in the limit comparison test. If that limit comes up a non-zero finite number, then I'm in business. That'll say that the two series either both converge or both diverge. And since we know this one converges, if that limit comes up a finite non-zero number, that series has to converge as well. On the other hand, if I go through all the work of doing that limit and it comes up 0, then this is not going to tell me anything. If I do the limit and it comes up plus infinity, that's not going to tell me anything either. I won't know until I've done the limit. The limit that's going to determine whether or not my effort is wasted is this limit. We can do one of three things. Firstly, we can look at it and say the limit is obviously 1. That's not a very satisfying way, though. Number 2, we could do the f of x trick version 1, or we could just do algebra on this, which I believe is what I'll actually do. Limits are tricky things. When is it legal to break this up into the limit of the top divided by the limit of the bottom? It's legal to do that when both of those limits exist and the one on the bottom isn't 0. As n becomes indefinitely big, the top of this thing approaches 1 plus 0 plus 0, which is 1. The bottom approaches 1 plus 0 plus 0 plus 0, which is also 1. Both limits exist. The one on the bottom isn't 0. The limit that we're interested in converges to value 1. The conclusion that we draw is that the infinite series we started off with converges due to the limit comparison test. Just as with the direct comparison test, though, you have to give it a reasonable comparison series. If I had decided to use as my comparison the sum of 1 over n, or the sum of 1 over n cubed, I would have ended up with one of those two cases where the limit comparison test doesn't tell me anything. So I have to pick some reasonable comparison, but having done so, I just have to calculate a limit. Let's look into the why of this. First, the direct comparison test. I'll assume that I've got some numbers, AI and BI, which are ordered in this way. The direct comparison test has two parts. Part number 1, what if the sum of the B numbers converges? By which I mean to an actual, honest-to-goodness, real number that I'm going to call capital B. We have previously figured out that every partial sum of the B series must be less than or equal to capital B. On the other hand, A1 plus A2 plus A3 out to AK is no bigger than B1 plus B2 out to BK, and those numbers are no bigger than capital B. I'm adding up positive A numbers, so this quantity is trapped between 0 and capital B. The partial sums of the A series form a bounded set. But there's more to it than that. The A numbers being positive means if I were to add up A1 through AK and then continue to add in A number K plus 1, so I'm getting partial sum number K plus 1 of the A series. Because A number K plus 1 is positive, this must be bigger than A1 plus A2 out to AK. The partial sums of the A series are not only bounded, but they're monotone also, which tells me the infinite series of the A numbers converges. This is half of the y of the direct comparison test. What we have figured out in 1a is this. If you have numbers that act this way, if the sum of those numbers converge, then the sum of those numbers converges. Part B will be, what if the sum of the AIs diverge? And we'll deal with that in a similar way. Suppose that the sum I equal 1 to infinity of AI diverges. Because the AI numbers are positive, a previously referred to fact tells us the way in which the series of A numbers diverges is that the partial sums have to become indefinitely big. Since each individual A number is smaller than the corresponding B number, it's obviously true that this sum can't be bigger than that sum, but that means the same thing as this sum is at least as big as that sum. Because of how the A series acts, if you give me a number h, no matter how huge it is, h is for huge, there's an index so that if I form a partial sum of the A series with index bigger than capital N, then A1 out to AK must be bigger than H. I can make the partial sum as huge as I care to make it. But the partial sum of the B series with the same index is at least as big, pardon me, is at least as big as the corresponding sum of the A series, which can be made as huge as you'd care to make it. That means the partial sums of the B series become indefinitely big as well. So if the sum of the things in the middle diverges, then the sum of the things on the outside diverges as well. This completes the argument, the logical argument, that this direct comparison test is as we said it was. Next, I want to establish that this limit comparison test works as we claim it does. I'm going to assume that I have two collections of numbers, an and bn. Again, in the whole setup, we're assuming that these numbers are positive. Suppose I calculate the limit as n tends to infinity of an over bn, and it turns out that that limit exists, it's positive, and it's finite. Everything's going to work because of what that statement means. What this means is if you crank the index up big enough on an over bn, you can make it as close to L as you want. To use a very specific thing, I can make this fraction less than 1 unit of distance away from L on the number line. So I'm going to think of my limit, my positive finite limit, L, as being here. L plus 1 is here. There is an index, capital N, so that if I'm looking at one of these fractions beyond that index, then I'm close to L. I am less than or equal to L plus 1, for instance. The 1 is not important. I could have used L plus 2 or L plus pi or whatever. These fractions, being fractions of positive numbers, are positive. So this inequality is true for all little n beyond some particular capital N. This inequality is true after a while. Multiply through by the positive number bn. Suppose that the sum of the b numbers converges. I think it's pretty clear then that the sum of L plus 1 times the b numbers converges as well. The ambitious might want to try to put all the details in for that. When you have a convergent infinite series, we have decided that it doesn't matter if you alter a finite number of terms as far as whether the series converges or diverges. So the fact that this infinite series converges means the same as the infinite series of these numbers if I start adding someplace other than 1. So that I don't get hung up on symbols, I'm going to phrase it this way. For indexes little n bigger than capital N, a sub n is positive, and a sub n is less than a term of a convergent infinite series. So the sum of these things converge starting at n plus 1 and going up to infinity. The direct comparison test says the sum of those quantities starting at little n equals capital N plus 1 and increasing must converge. But once again, we have said that altering a finite number of terms of an infinite series doesn't affect its convergence or divergence. I could think of this infinite series as being the A infinite series, where someone has set the first capital N terms to 0. If I put them back to the value they started off being, it doesn't affect convergence or divergence. So if the hypotheses of the limit comparison test are true, this must be true beyond some index. If the sum of the B quantities converge, the sum of those quantities converge, the sum of those quantities converge because this is the same series as that with some terms set equal to 0. That means for little n bigger than capital N, a sub n is trapped between 0 and the terms of a convergent series. I'll use the direct comparison test to conclude that that infinite series converges, which, because of the change the finite number of terms thing, tells me that the A series converges. This is half of the limit comparison test. If you're observant, you'll notice something here. I never have made use of the fact that L isn't 0. So in the setup so far, even if the L was 0, if the B series converges, so does the A. Before going on to the other half, I might as well look at the situation where the sum of the A's diverge. Then that means even though I leave out the first n terms, the sum of these things would have to diverge as well. The sum of L plus 1 B sub n, starting at capital N plus 1 and up, would have to diverge. L plus 1, even if L were 0, is positive. That would mean that B capital N plus 1 and so on must diverge, and that would give me another chunk of the limit comparison test. So what we know so far is this. If the condition in the limit comparison test is true, then if the B series converges, the A series converges. If the A series diverges, the B series diverges. To get the other half, suppose that the limit as n tends to infinity, an over bn is L, where L is positive and finite. Informally, that means when the index little n is very big, an over bn must look a lot like L. Of course, you can turn that around backwards. Bn over an would have to start looking a lot like 1 over L. So this is where I need the L to not be 0. For n sufficiently large, the fraction bn over an cannot differ from 1 over L by much. If you increase the index sufficiently, you can make bn over an no more than 1 over L plus 1. If you multiply through by the positive number, a sub n, you will get this inequality. This should look very familiar to you. If I have two infinite series and their terms are related in this way, if the sum of these converges, then the sum of those converges. This is the direct comparison test again. If the sum of those diverge, then the sum of those diverge. Don't get hung up on the names of things. A and B are just names. Also, L plus 1 is just some positive number. 1 over L plus 1 is just some positive number. In the previous work, the A numbers were there, the B numbers were there, and that positive number was L plus 1, none of which makes any difference. If the sum of these things converges, then the sum of those things converge by the direct comparison test. If the sum of those things diverge, then again, by the direct comparison test, the sum of those things diverge. Since only the names of things have changed and not the logic, that's all I'm going to say about that one. So, to summarize, we have figured out the what of the direct comparison test and the limit comparison test. We see how to apply them. We have also seen why these things are true. We want to look at something called absolute convergence and alternating series. Then everything that we've talked about in terms of this theory stuff up to this point will all come together and give us what's called the root and ratio test. This will be our complete package of how to decide if infinite series converge or diverge. After that, we will wrap stuff up by looking at power series. In the meantime, I hope everybody has a good day. I'll talk to you again soon.